Hello and welcome back to JKSSB Olympiad, a global hub for engineering tutorials, the very classroom style. We're going to start the new chapter, weight and volume relationships. We'll be doing the MCQs as well as the numerical questions. In this part, we shall be doing the MCQ questions, and later on, we'll also try to solve as many numerical questions as possible. So let's start. Weight volume relationships. This is the second chapter that we have started for the geotechnical engineering, and so let's start the MCQs. The first question is, all right. The volume relationships commonly used for the three phases in a soil element are. First option is, we have to choose the most appropriate option. The first option is void ratio and porosity. Second one is moisture content and unit weight. Third one is degree of saturation and moisture content. And the last one is void ratio, porosity, and degree of saturation. The volume relationships commonly used for the three phases in a soil element. We know that the soil mass consists of solid particles which form a porous structure, and it's generally a three-phase system. And the voids in the soil mass, they are filled with air. Voids are filled with air, with water, or partly with air and partly with water. Partly with air and partly with water. All right. So this soil mass, it is a three-phase system generally. It is a three-phase system containing one, the soil solids, second, the voids in which there can be air and water. So the soil is generally a three-phase system, but it becomes two-phase system also. It becomes two-phase system when in two cases. First one, when the soil is absolutely dry, there is no water phase. So soil mass becomes a two-phase system with soil solids, and in voids there is air. All right. And second condition is when the soil is fully saturated. When the soil is fully saturated, the air phase disappears. There is no air phase. So again, in this case, the soil system, it becomes a two-phase system. Soil mass becomes a two-phase system with soil solids, and voids are filled with water. So let me again repeat it, that generally soil mass is a three-phase system with soil solids, and the voids, they can be filled with air and water, or partly with air, partly with water. And under some special conditions, it becomes a two-phase system. The first one being when the soil mass is absolutely dry, there is no water phase. So in that case, it becomes a two-phase system with the soil solids and voids are filled with air. And the second case is when the soil mass is fully saturated, there is no air phase. So again, in this case, soil mass becomes a two-phase system with soil solids and voids are filled with water. So coming back to the question, what does question say? The volume relationships commonly used for the three phases in a soil element are. All right. We have to say it keenly. The volume relationships commonly used for the three phases in a soil element are. So the appropriate answer and the correct answer is option D. It's true that the volume relationships commonly used for the three phases in a soil element are void ratio, porosity, and degree of saturation. All right. Moving on to the next question. Next question is, the common terms used for weight relationships are. Option 1 is void ratio and porosity. Second one is moisture content and unit weight. Third is degree of saturation and porosity. And the fourth one is none of the above. The correct answer is option B. The common terms that are used for the weight relationships are moisture content and unit weight. Please bear with me, my throat is unwell. All right, so the common terms used for the weight relationships are moisture content and unit weight. Option B is the correct answer. All right, moving on. Question number 3. As already discussed, soil mass is generally a two-phase system, three-phase system, single-phase system, or none of the above. Soil mass is generally a three-phase system, but under some special conditions, it becomes a two-phase system. The first one being when soil is completely dry, there is no water phase, there are only two phases, soil solids and the soil air. Voids are filled with air. And the second condition is when the soil is fully saturated, there is no air phase. In that case also it becomes a two-phase system with soil solids and the voids are filled with water. But generally the soil mass is a three-phase system with soil solids and the voids can be filled with water and air. All right, moving on to the next question. All right. With regard to the void ratio, which statement is correct? We have to see with regard to the void ratio, which statement is correct. First one, for coarse grained soils, the void ratio is generally smaller than that for fine grained soils. For coarse grained soils, the void ratio is generally larger than the fine grained soils. The void ratio is generally same for coarse grained and fine grained soils. None of the above. All right. Before moving to the question, let's see what void ratio is. Void ratio is a very important, very important volumetric relationship in case of a soil sample. And void ratio, what does it mean? Void ratio is defined as a ratio between volume of voids to the volume of solids in a soil mass. All right, void ratio is a very important volumetric relationship in a soil mass, and it's defined as the ratio of volume of voids to the volume of solids. All right, and it's denoted by E. So E is equal to volume of voids divided by volume of solids. All right, and the void ratio is expressed as a decimal. All right, we don't usually express it as a percentage, rather we express it as a decimal, such as 0.4, 0.5, etc. And it must be noted that for coarse grained soils, such as sands and gravels, this void ratio is generally smaller than that for the fine grained soils. All right, void ratio, which is a very important volumetric relationship in a soil mass, and it's defined as a ratio between volume of voids to the volume of solids in a given soil mass. And this is usually expressed in terms of a decimal, and not usually, we don't express it as a percentage. And it must be noted that for coarse grained soils such as sands and gravels, the value of void ratio is generally smaller than that for the fine grained soils. And it must also be noted that for some soils it can have value even greater than unity. Right? For some soils, the values of void ratio can even exceed unity. All right. So coming back to the question. Question is, with regard to void ratio, which statement is correct? For coarse grained soils, the void ratio is generally smaller than that for the fine grained soils. This is the correct answer. All right. It must be noted that for coarse grained soils, the void ratio is generally smaller than that for the fine grained soils, such as clays. All right. Moving on to the next question. All right. Question is about degree of saturation. And the question is, the degree of saturation is equal to 0 when? The degree of saturation is equal to 0 when the soil is fully saturated, when the soil is absolutely dry, both A and B, or none of the above. Degree of saturation, this is also very important volumetric relationship in case of a soil mass. Degree of saturation, it is denoted by S. All right, and it's defined as the ratio between volume of water to the volume of voids. All right, degree of saturation is also one of the most important volumetric relationships, as was the void ratio, and it is a ratio between volume of water to the volume of voids in a given soil mass. All right, and it's also expressed as percentage. Unlike void ratio, which we usually express as decimals, this is degree of saturation is generally expressed as a percentage, and it becomes 0. This is the ratio, volume of water to the volume of whites. When shall it become 0? It will become 0 when the soil is absolutely dry. When the soil mass is absolutely dry, volume of water is nil in the whites. So it becomes 0. Degree of saturation becomes 0 when the soil is absolutely dry, and it will become 100% since we express it as a percentage. It will become 100% when the soil is fully saturated. That means entire voids are only filled with water. There is no air phase. Alright, in volume of whites there will be no air phase, so it will become 100%. Volume of water will be the only volume in the whites in that soil mass. Since it is fully saturated, there is no air phase, so in that case the degree of saturation will become 100%. When the soil is fully saturated, and it's equal to 0 when the soil is absolutely dry, there is no volume of water in the whites. All right, so this was about the degree of saturation, which is very important volumetric relationship, and it's a ratio between volume of water to the volume of whites in a given soil mass. Coming back to the question, so the question says the degree of saturation is equal to 0 when we already learned when the soil is absolutely dry. So option B is correct option. All right, moving on to the next question. Question number 6, all right, is again about degree of saturation. The degree of saturation is 100% when the soil is fully saturated, the soil is absolutely dry, both A and B, or the none of the above. We already learned herein that the soil mass, when it's fully saturated, there is no air phase. Entire volume of the voids, there will be only water. So the degree of saturation will become 100% since it's a ratio between volume of water and the volume of voids. All right. So the answer is the degree of saturation is 100% when the soil is fully saturated. When the soil is fully absolutely dry, the degree of saturation is 0, and when the soil is fully saturated, the degree of saturation is 100%. All right, moving on to the next question. We are studying the weight-volume relationships. It's a very important chapter in geotechnical engineering, and we are studying it by solving multiple choice questions, and following that we'll also be solving as many numerical questions as possible. All right, so stay tuned to Engineering Olympiad. All right, next question. When the soil is fully saturated, air content is 0, percentage air voids is 0, both air content and percentage air voids is 0, none of the above. All right, so before moving to this question, we have to learn about this thing: percentage air voids, air content. All right, so let's see. These are also very important volumetric relationships in case of a soil mass. Let me write it down here first. There are 5 very important volumetric relationships in a soil mass. The first one being void ratio, which we already learned that it's a ratio denoted by E between volume of voids to the volume of solids. Second one is porosity. It's denoted by N, and it's a ratio between volume of voids to total volume. Third one we learned, it's degree of saturation. Degree of saturation. All right. Degree of saturation, and it's a ratio denoted by S, and it's a ratio between volume of water to the volume of voids in a given soil sample. Next one is percentage air voids. Percentage air voids. And the last one, fifth one, is air content. This percentage air voids, it's denoted by NA, and it's also a ratio between volume of air to the total volume in a given soil mass. And air content, it is denoted by A, C, and it's also a ratio between volume of air to the volume of voids. All right, so these are the 5 very important volumetric relationships in a given soil mass: void ratio, porosity, degree of saturation, percentage air voids, and the air content. These are all ratios between voids and solids and water phase, generally between the 3 phases in a soil mass. All right, so percentage air voids and air content, let's come to them. These ratios, percentage air voids and the air content, these will be 0 when both air content and the percentage air voids will be 0 when the soil is fully saturated. When the soil is fully saturated, there will be no air phase, so both air content and percentage air voids, they will become 0. All right, so coming back to the question, when the soil is fully saturated, air content is 0. Is it true? Definitely yes, because air content is a ratio between volume of air to the volume of voids. And when the soil will be fully saturated, there will be no air phase, so air content will be 0. True. Percentage air voids is 0. Percentage air voids is a ratio between volume of air to the total volume, and when the soil will be fully saturated, there will be no air phase, so the percentage air voids will be 0. True. Both air content and percentage air voids are 0 when the soil is fully saturated. This is the correct option. All right, so when the soil sample is fully saturated, there will be no air phase, so both percentage air voids, since they contain volume of air in numerator, it's a ratio between percentage air voids is a ratio between volume of air to the total volume, and air content is a ratio between volume of air to the volume of voids, since they contain volume of air in their numerators, so both will become 0 when the soil is saturated. Fully saturated, there will be no air phase. All right, so option C is the correct option. All right, moving on to the next question. All right, question number 8. With regard to the water content, which statement is true? First one, water content of fine-grained soils is generally more than that of the coarse-grained soils. Water content of fine-grained soils is generally less than that of the coarse-grained soils. Water content is generally same for coarse and the fine-grained soils, or none of the above. All right, we have to choose the most appropriate option. But before moving to the question, let's study about this thing, water content. All right, water content, it is denoted by W, and it's defined as the ratio between mass of water to the mass of solids. All right, so in a given soil sample, the ratio between mass of water to the mass of solids, this is known as the water content. All right, this water content is also known as the moisture content. And it's expressed as percentage, but it is used as a decimal in computations. All right, and it must be noted that the water content of the fine-grained soil, such as silts and clays, it is generally more than that for the coarse-grained soils, such as gravels and sands. So the water content of the fine-grained soils is generally more than that of the coarse-grained soils, and the water content of some of the fine-grained soils may even be more than 100%. It may even exceed 100%. In case of some of the fine-grained soils, this water content can even exceed 100%. What does that indicate? That indicates that more than 50% of the total mass is that of water. All right. So the water content is defined as the ratio of the mass of the water to the mass of the solids. All right, it's also known as the moisture content and is generally expressed as percentage but used as a decimal in computations. And it must be noted that for the silts and clays, that's for the fine grained soils, the value of this water content is generally more than that of the coarse grained soils such as gravels and sands. All right, so coming back to the question, which statement is appropriate? Water content of fine grained soils is generally more than that of the coarse grained soils. Option A is the correct option. All right, moving on to the next one. All right, it is about the net mass of soil in submerged conditions. All right, so the question is, the net mass of soil when submerged is reduced, increased, remains same, or none of the above. All right, when the soil exists below water, when soil exists below water, we say that it is in submerged condition. We'll say that it's in submerged condition. And when the volume V, let's suppose, of the soil is submerged in water, it displaced an equal volume of water. So definitely the net mass of the soil when submerged, it will be reduced. All right? Because when the soil exists below water, it is in submerged condition. All right? And a buoyant force will act on the soil solids. Buoyant force. It will act on the soil solids. And we know that according to Archimedes' principle, the buoyant force, it is equal to the weight of the water displaced by the soil solids. According to Archimedes' principle, the weight of the water displaced by soil solids is equal to the buoyant force that acts on it. So the net mass of the solids is, net mass of solids will be reduced. This reduced mass is known as the submerged mass or the buoyant mass. This reduced mass of the soil when it's in submerged condition, this reduced mass is known as the submerged mass or the buoyant mass. All right, coming back to the question. So the net mass of the soil when it's in submerged conditions or when it's submerged is reduced. Option A is the correct answer. All right, moving on to the next one. All right, question says the specific gravity of solids for most natural soils falls in the range of 2.65 to 2.80, 3.12 to 3.50, 1.65 to 2.10, or 0.87 to 1.11. All right, before moving to the question, let's study about specific gravity. Specific gravity of solid particles in a given soil mass, it is denoted by G, and it's also a ratio between mass density of solids to the mass density of water. All right, it's defined as the ratio of the mass density of a given volume of solids to the mass density of an equal volume of water, and that too at 4 degrees centigrade. All right, and the mass density of water, we know it's equal to, at 4 degree, very important, it is equal to 1 gram per milliliter or 1000 kgs per cubic meter or 1 milligram per cubic meter. This is the mass density of water at 4 degree centigrade. All right, and it must be noted that the specific gravity of solids for most natural soils they fall in the range of 2.65 to 2.80, and the smaller values are for the coarse grain soils. Smaller values for coarse grain soils such as gravels and sands. Alright. So the specific gravity for most natural soils fall in the range between 2.65 to 2.80, with the smaller values being for the coarse grain soils. Alright, so coming back to the question. The specific gravity of soils for most natural soils, it falls in the range of, option A is the correct answer, it falls in the range between 2.65 to 2.80 for most natural soils. Alright, so this was about specific gravity of soil solids, which is defined as the ratio between mass density of the soil solids to the mass density of the water, of equal volume of water, and that too at 4 degrees centigrade. Alright, so this was about the specific gravity. Alright, next question is also the same. With regard to specific gravity, which statement is correct? Larger values for coarse grain soils, smaller values for coarse grain soils and fine grain soils, they exhibit equal values, or none of the above. We just studied that the values for the specific gravity, they're generally smaller for the coarse grain soils. Alright, so the option B is the correct answer. With regard to specific gravity, we have smaller values for the coarse grain soils such as gravels and sands. And it must also be noted that for most of the natural soils, the range of the specific gravity, it lies between 2.65 to 2.80, with the smaller values being for the coarse grain soils. So option B is the correct and the most appropriate answer. Alright, moving on to the question number 12. The wide ratios of natural sand deposits depend upon shape of the grains, uniformity of grain size, conditions of sedimentation, or all of the above. The wide ratios of the natural sand deposits, it depends on all these conditions. So all of the above is the appropriate answer. It depends on the shape of the grains, it depends on the uniformity of the grain size, and it totally depends on the conditions of sedimentations as well. Alright, so the wide ratios of the natural sand deposits, they depend upon shape of grains, uniformity of grain size, and the conditions of sedimentation. So the option D is the correct option, all of the above. Wide ratio, very important volumetric relationship, denoted by E, and the ratio between volume of voids to the volume of solids in a given soil mass. Alright, moving on to the question number 13. Alright, it's about pycnometer. And the question says, pycnometer is used for water content determination of soil sample, specific gravity determination of a soil sample, both A and B, or none of the above. Alright, so we have to see which is the correct answer. This pycnometer, before moving on to the question, this pycnometer, it is a glass jar of about 1 liter capacity. This pycnometer is a glass jar of about 1 liter capacity, and it is fitted with a brass conical cap. Brass conical cap by means of a screw type cover. Alright, and this cap has a small hole of 6 mm dia at its apex, and we use a rubber or a fiber washer between the cap and the jar so as to prevent the leakage. Alright, so a pycnometer is typically a glass jar of about 1 liter capacity and fitted with a brass conical cap by means of a screw type cover, and this cap has a small hole of 6 mm diameter at its apex, and we fix a rubber or a fiber washer so as to prevent the leakage between the cap and the jar. Alright, And this pycnometer, it is used to determine both specific gravity as well as the water content for a given soil sample. Pycnometer is used for water content determination of a soil sample, and it's also used for the determination of specific gravity of a soil sample. But one thing must be noted, that when we use pycnometer to measure the water content, it can only be used if the specific gravity of soil solid particles is known to us. Since pycnometer, it is used for both water content determination and checking of specific gravity of soil solids in a given soil mass. But it must be noted, then while we use pycnometer for the water content determination of a soil sample, it can only be used when this thing is known. Alright, so the pycnometer method for the determination of water content can be used only if the specific gravity of soil solid particles is known beforehand. Alright, so let's move to the question. Option C is the most appropriate answer. Pycnometer is used for both water content determination of a soil mass as well as specific gravity determination of soil sample. Alright, moving on to the next one. Question number 14. Alright. We have to state whether these statements are true or false. The first one is the water content of soil can be more than 100%. Alright. We just studied about the water content. And water content, it's a ratio. Let me write it here. Water content is a ratio between mass of water to the mass of solids. Alright. And it's also known as the moisture content, and it is expressed as a percentage but used as a decimal in computation. Now the question is, can it be more than 100%? Yes, we just studied that the water content of the fine-grained soils such as silts and clays is generally more than that of the coarse-grained soils, and the water content of some of the fine-grained soils. Water content of some of the fine-grained soils may be even more than 100%. It may even exceed 100%, which indicates that more than 50% of the total mass is that of the water. More than 50% of the total mass is that of the water. Alright, so this statement is absolutely correct and true. The water content of soil can be more than 100% if the weight of the solid exceeds the weight of the dry soil solids. If the weight of the water exceeds the weight of the dry soil solids, the water content becomes greater than 100%. Alright, since it's a ratio between mass of the water to the mass of the soil solids. Alright, and if this exceeds the weight of the dry soil solids, then this will exceed 100%. And this commonly occurs in highly compressible fine-grained soils such as soft clays, organic soils, and peat, etc. Alright, so this is already known to us that in certain fine-grained soils, like the ones which are highly compressible, like that of the soft clays, organic soils, and peat, etc., this value, water content, its value can exceed 100%. Alright, let's take an example and see over here if this thing is true. Let me rub it first. Alright, I'll let you know by means of a small numerical. Alright, question is, if a soil sample contains 120 grams of water and 100 grams of dry soil solids, the water content of the soil will be All right. So water content is the ratio between mass of water to the mass of the solids. And in this question, it says if a soil sample contains 120 grams of water and 100 grams of dry soil solid. So the weight of the water exceeds the weight of the dry soil solids. So definitely the value will be more than 100%. 120%. All right. So we just studied by means of a numerical that yes, it's absolutely true that in certain cases the water content of soil can be more than 100%, and this thing generally happens in case of highly compressible fine grained soils such as soft clays, organic soils and peat.